Here we've got an example of a word problem you could see. So this is saying this kid Felix's parents called him home, and they say come home immediately. He leaves his friend's house and makes it back to his house, which is 13 miles away, and he makes it in 15 minutes. Then his parents are like, hey dude, you broke the speed limit, which is 45 miles per hour. And then they want us to use some logic to say, well, how do we know that this kid was speeding coming home right now? This is, you read it, you should say, okay, I'm looking at a physics problem right now, right? We've got position, we've got velocity going on right here. So velocity we know is a derivative. It's the derivative of our position function. And then the other thing you're always going to have in these is sort of an average velocity. So the velocity between your starting point and your ending point, right? And so we can get an average velocity by doing sort of our y2 minus y1 over x2 minus x1 situation. To do that, we need to know the endpoints. Well, on these position problems, remind yourself that usually you're starting at time 0, and your distance, you haven't gone anywhere yet, so your position would be 0. So that's sort of an implied point that they usually give you in one of these problems. Then they give us a second point basically right here, where we're at 15 minutes, and in 15 minutes, we are a distance of a position of 13 miles per hour. And then, like we said, when we started this, we were given 45 miles per hour for what our velocity is. Quick check on these problems you always want to do is, what are the units? Oftentimes on these velocity problems, they'll give you time in minutes, but then they'll be talking to you about miles per hour, right? So really, we don't want 15 minutes for our time. We need that time to be in hour terms. So 15 minutes would be 0.25 hours. And in 0.25 hours, you've gone that distance of 13 miles. So just watch out for little nuanced pieces like that. Now that I know what I'm looking at, there's a classic mean value theorem. Whenever you need to compare the average to an instantaneous, which is what a derivative is, right? An instantaneous rate of change, that's when your mean value theorem comes into play. The mean value theorem, if you don't know it right now, you're going to want to know it. So the mean value theorem says if you've got an equation that is continuous on the x interval, some x interval a to b, and differentiable, it's got to be both of these things. Differentiable on the open interval ab. If you can tell me that that is true, then you get to draw this conclusion. Then you know that there is a point C, a value C, an x value, that lives between A and B, that is somewhere in between A and B, such that the average rate of change between our two endpoints will equal the instantaneous rate of change at that specific C value. So what we know is our average rate of change, our AROC, our average velocity in this situation, is going to be equal to our instantaneous rate of change, our actual velocity, at one specific point, at some point C. So to prove that, you have to run through kind of a standard little mean value theorem setup. Step one when you're doing a mean value theorem is really you got to show them or tell them that you know that the if portion of this thing is continuous. So what you know is you're dealing with a position function. And so you would say position is continuous on the closed interval. So our closed interval, we're starting at 0, we're ending at 0.25. So position is continuous on the interval from 0 to 0.25 and also differentiable on that same interval. Remember, you're not going to just be jumping around in space. The only way to get from 0 to anywhere is going to be by getting 0 to 5. If you walk 5 feet, you had to get every portion of 5 feet in between 0 and 5. So we know it's continuous. You're not going to jump through space. And then it's differentiable because there's no jumping, no jerking movement. So it's continuous and it's smooth. So we have our if portion. And what that tells us is we now get this conclusion down below here, that our average rate of change is got to equal our velocity, our instantaneous rate of change at some point. So the first thing you'll do is you just need to go find out what is that average rate of change. Average rate of change is just fancy math talk for slope as you've always known it. So y2 minus y1 over x2 minus x1. Our first point, our x1 and our y1 is that 0, 0. Our second point, our x2 and our y2 is where we ended up, 0.25 and 13. So popping those into our equation, we get y2, which is 13, minus y1 over x2, which is 0.25, minus x1, which is 0. And so out of there, we get 13 divided by 0.25, which is going to equal 52, and that's in miles per hour. So we get out of there 52 miles per hour. Well, by the mean value theorem, we basically get our final conclusion here. By the mean value theorem, MVT, we know that that average rate of change, 52 miles per hour, somewhere in between there, it had to equal the instantaneous rate of change, which in this model is your velocity. So your parents don't know when you were speeding, but they knew that you were speeding because at some point in between, the velocity has to equal your average rate of change. So at some moment, you were going over that speed limit. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.